quiz number 3 plus homework assignment. So this weekend, after you submit, then I grade it. So the next meeting, Monday, so I will do the review number 2, covering quiz number 3 and the homework assignment. Then Wednesday midterm, right? Yeah, Wednesday midterm. Oh, sorry, not Wednesday. Thursday, sorry. Yeah, I got confused. Thursday midterm. Try to arrange your schedule. For you, probably okay. For a few students, those students, yeah, because I remember several students rarely come to the classroom. Those students probably they need to make an appointment with the testing center. All right, so let's start. Part 1, explain questions of quiz 1. For a relatively simple question, I can move a little faster. We will squeeze a little more time for the homework assignment. The first one, is the execution time of a program stable, measured? Answer is no. In the class, I explained that. Yeah. The reason it is not stable because we consider different machines have different computing power. Some machine, supercomputer, high-end, they can do much faster. For some computers, low-end, 10 years old, even, relatively slow. So you cannot compare those computers using this execution time directly. Then, once they ask one question, because in our project number 1, remember, we compare execution time, right? Method 1, method 2. But it's on your same machine, right? Yeah. So the same base, same machine. So there we are fine, right? Yeah. So we do not compare those two numbers on different machines. Yeah. So in that way, even unstable measure, but we can still use it in the right way, right? So do not get confused, okay? So do not get the impression if it's unstable, so we should never use it, right? Do not get that kind of impression. Unstable, but we should use it in a limited way, right? Restricted way, okay? Yeah. So we control the condition, how to use it. So that's the first question. Right? Yeah. The second one, answer pretty simple. Yeah. Because in class I mentioned it. And also, that should be your basic knowledge, right? 1 billionth. So 10 to the negative 9th power. So that's the option C. Okay? Yeah. So for questions like this, usually I treat as the simple question, just give you some easy points. So every assignment or test, usually I give you 2 or 3 questions like this. Okay? Simple, straightforward answers, but do not expect other answers also like this, straightforward, simple. Other answers, many of them pretty challenging. So you need to really, use your brain, logical reasoning, do some hard work. So you can see in the homework assignment, some questions pretty hard. All right, for this question, what I like you to do, here I like to point 2 ways to solve this one. One way, we just apply our standard formula. Remember this formula, we apply it again and again. And that is 1/2 n plus 1, right? So this formula, our standard formula, for this question, because we do not start from 1, but can you split into 2 parts? How about we calculate the first summation, start from 1, but because we add first few consecutive integers, we should do subtraction. Right? Yeah. Then we get the same summation. Okay? But in this way, you can see we can apply our above standard formula twice. The first time, plugging in that formula, when n equals 27, and get 8. The second one, n equals 6, 7. Okay? So now you can find the answer. This is method 1. Okay? Method 1. But there is another simple way. If some of you, some students, so if you have a little more background knowledge, you read many different books, so you have broader knowledge background, then those students probably know another formula. Okay? The formula is this. You apply that formula directly. 1/2 times the first number plus the last number. So 7 plus 27. Then times the number of summon, the number of operands. Okay, how many? Do not count it wrong. If you count it wrong, you get wrong answer. Do not use 27 minus 7. If you use 27 minus 7, you missed by 1. Okay? So you use 27 minus the number right before 7. That's 6. Right before that, 7. So 27 minus 6 equals 21. Okay, so you should put 21. Okay? So in this way, you can also find the right answer. This way corresponds to finding the area. Remember, finding the area of trapezoid area. In your middle school geometry class, all right? Yeah. The top side A, bottom side B, the height H. What is the area? Area 1/2 A plus B times H. Okay? Yeah. What's A? The top side. Okay? That's our 7 top side. Okay? What's the bottom side? 27. That's the bottom side. What is the height? Number of operands. Okay? Number of operands. You need to count. How to count? 27 minus 6. Do not use 27 minus 7. After you pay attention to details, a few places, then you get correct answer. So you see, with this simple example, your knowledge background is important. You need to have some knowledge background. Okay? All right. Yeah. So that's this question. Number 4, given a chessboard, we want to find those squares of different sizes with 4 dark squares at its 4 corners. How many such squares can you find? You need to bring up the chessboard, that picture. Here, I put it here, right? Yeah. Then, yeah, try to find the rules, how to calculate those squares. Here, for example, this one, this 3 by 3 square, 4 dot squares and 4 corners. All right. So, but its size is 3 by 3. Here, we consider size 3 by 3. Okay, all right. Then the horizontal, how many can you find horizontally? Right? 3 by 3, the next 3 by 3, then the last 3 by 3. Okay? Yeah. Horizontally, you get 3. Vertically, the first one, the second one, the third one. Sorry. Yeah, the third one is this. Okay? Vertically also 3. Okay? Yeah. So vertically also 3. All right. 3 by 3. All right. But other than that, next round, 5 by 5, yeah, there is another half. We will go to that part later. Okay? So 5 by 5, horizontally, yeah, it's here. Horizontally, the first 5 by 5, okay, horizontally, and the second 5 by 5, okay, second 5 by 5, all right, so 2 by 2, horizontally, vertically also 2, okay, all right, then 7 by 7, okay, 7 by 7. Horizontally, vertically, 1 by 1. Okay, all right. But if you look at this part, there is another symmetric, you know, like mirror reflection. If you look at based on this diagonal, do the mirror flip, okay? There is another copy of the same set of figures, same set of figures. So you can just multiply by 2. Because symmetric, mirror flip, okay? Yeah. Against the diagonal. So if you can see that, then the calculation, well, so 1 plus 4 plus 9, 14 times 2, then you get 8. Okay? In this way, this question checking you several skills, observation, and the data organization. Observation, you need to find properties. What properties that require figures should have? Second, how to organize your data. 3 by 3, 5 by 5, 7 by 7, and mirror flip also. So then, put those pieces together so you can get the right answer. Okay? Yeah. All right. Next question. For this one, the formula, how to find the correct one. Plug in simple numbers. plug in simple numbers to eliminate. If the answer is incorrect, then eliminate it. That's the goal. Okay? Alright. So when n equals 1, the correct one, because here only 1 square. So the answer is 1. Now you plug in the first of 4 options. Because E, we will see at the end. The first one, A, 1 times 2 times 3, that's 6. Then multiply 1/2, that's 3. 3 not equal to 1, right? So A is gone. Plug in B, yeah, so 1, 2, 3, then multiply 1/6. So it's 1. It's 1. So we leave there. We leave there temporarily. C, 1/2 times 1, 2, 5, cancellation, and 5. 5, gone. Okay? Yeah. So the first round, A, C are eliminated. D, 160. 1 times 2 times 3, 160. That's 1. So B and D left after first round elimination. Second round elimination, n equals 2. Okay? Plugging into that B, 2 times 3 times 4, that multiply. So the answer is 4. Yeah. But here, n equals 2, the first two terms, 1 plus 4 squared equals 5. 4 and 5 different. So B is eliminated. Okay? Yeah. So D should be correct, but let's verify the last time. Okay? Alright. So 2 times 3 times 5, 2, 3, after cancellation, 5 left. Yeah. Looks still correct. Yeah. After the second round elimination, it's still correct. So then we can say, the most likely D is correct. Okay? Because here I have to give you one correct formula. So you can, select D. I don't want to trick you. Okay? I don't want to, put a garbage formula passing first 2 rounds eliminations, but still wrong. Okay? Yeah, I don't want to trick you. All right? Yeah. So you can, select D with confidence. With confidence. Okay? All right. So based on this, remember we apply the strategy. Do experiments on simple cases. We do experiments on simple cases. 1, 2. That's enough. Okay? I do not ask you to prove it. Okay? I do not ask you to derive the formula. Although that's a good exercise, but too much work. Okay? Too much work. All right, number 6. Given polynomial with n plus 1 coefficients and the variable x for a positive integer n, we only have one way. Based on our nodes, our project, we have 2 ways, right? Brute force corners. That's simple. Yeah. So it's false. Okay. Simple question like that. Okay. All right. How many terms can you find in the following polynomial? Yeah. But here the terms given not using the consecutive exponent numbers or subscripts. But we need to figure out the rules. So the subscripts, exponent numbers the same, which is one of it, but we need to find the rules. 3, 7, 3 plus 4. The difference is 4. Okay? 3 plus 4. 11, 3 plus 8. So that is 3 plus 2 times 4. And so on. Okay? Until we get 295. So the subscript or exponent, so we can use the formula. So let's use the exponent. Okay? T equals 3 plus 4k. So how about that? 3 plus the 4k. So that's the observation we have from this question. Then we need to find the range for k. The smallest k and the largest k. The range for the k. Okay. The smallest k, 0. Right? 0. 4 times 0. The largest we need to figure out. Okay? The largest because 295 equals 3 plus 4k. So k equals 292 over 4, 73. So from 0 through 73, consecutive integers starting from 0 through 73 inclusive. Include 73. How many of them? Do the counting. Counting by reference. How many? 74. Not 73, 74. Okay, 74. Yeah. One student showed me she put 73 there. Okay. Yeah. Because when you see 73, 0, you just put 73, but you didn't count 0. Right? Yeah. So here, if you can go back check your answer. If you put 73, I can give it partial credit. Okay, 2 points partial credit. But you need to take the screenshot. Send me your screenshot. Then I will add 2 points back to this one score. Okay. All right. Question number 8. Polynomial degree 200. The highest term A200 times x to the power of 200. How many multiplications do we need if we apply ordinary rule? We know the same degree number, right? If the coefficient is not 1, here, when you apply the ordinary rule, you need to check the leading, we call it leading coefficient. Yeah, here it's a general. Because it's a general number, so it's another constant 1. If it's constant 1, you need to minus degree minus 1. Okay? Yeah. Because the last multiplication you do not need to do it. That's 1, why you need to do another multiplication? But here it's a general number, not a 1. So we need to do that same number of multiplication. That is 200. Okay? Yeah. So that's one difference, but we try our best to write the answer. Okay? Even one difference. All right, number 8. Number 9, in order to derive the ordinary rule for the polynomial evaluation, which of following mathematical operations is useful? So you need to go through the whole procedure, how we derived the ordinary rule. Factorization, right? Remember common factor, we factor out the x, that's the common factor, factorization. Question?
Give me I want to see
Bring down.
Previous question, which you explained.
Yeah, previous. This one,
Yeah.
previous.
Okay, I got it. Thank you.
All right. All right. Yeah. So here, not just to memorize the results we derive. I hope you follow the whole story from beginning to end. When we derive some result, you also need to be familiar with the procedure, the whole procedure. Because in that way, you can, expand your knowledge background. That part could be useful. Okay? Could be useful. So the whole story also important. Last question of this one. Is it possible that Walker's rule may not give you the best solution? Yeah, it's possible because after we learn repeated squaring, repeated cubing, those two techniques, then this answer very easy. Okay? Repeated squaring, repeated cubing. Yeah. Later we have another question comparing these two. In quiz 2. Okay? But here, just easy answer. Okay? Yeah. That's what we have. Certain. Yeah. Remember here, I use certain. I do not use the general polynomials. General polynomials, Horner's rule the best. Okay? Certain because we can consider special polynomials. Right? We can consider special polynomials. So we can apply repeated squaring, repeated cubing. If I give you the general polynomials, then Horner's rule is the best. Okay, that difference. All right. R.2 questions of question. The first one in the polynomial evaluation problem, basic operation. Which one? Now, check your understanding of basic operation. Multiplication. Multiplication dominates the addition. If we look at the number, for addition, we only need an n, right? N. Multiplication, although by Horner's rule, we also get an n. By Horner's rule, we also get an n. But we know multiplication much slower than addition, right? Still, the execution time we spend on multiplication dominates the amount of time we spend on addition. Remember, I give you approximately 10 to 1 ratio. 10 to 1 ratio. Okay? That's pretty close, not exactly 10 to 1 ratio. So you can get approximately 90% of the execution time if we apply Horner's. 90% of the execution time we spend on multiplications, only 10% of the time we spend on additions. All right. L'Hopital's rule. When we calculate the limit of the ratio of two growth functions, we can always apply L'Hopital's rule. Remember, a key condition, indeterminate form. For this class, we only consider infinity over infinity. Indeterminate form. Right? Then you can apply. But another thing, you never change from discrete variables to continuous variables. That's also important. Okay? So when you apply it, be careful, because we're not satisfied just with the correct answers. We want to do things right. Every step, we want to do things right. So we do that conversion. Discrete variable to continuous variable conversion. That means from variable n to variable x conversion. And when you take derivatives, no problem. No problem. All right. Next one. Given a computing problem, if you have an algorithm to solve it, and nobody in the world can improve it anymore, then you can say that your algorithm is optimal. Here, I try to, give you some illusion to the wrong answer. Check if your understanding of the optimality is very solid. The answer is false. The answer is false. Here it looks like the condition is quite strong, right? I tried to make it. It looks strong. I tried to make it look strong, but actually it's not strong enough. Still not strong enough. Okay? The reason is this condition is still not strong enough. Why? Okay?
So what condition is strong?
Yeah, I will get there. Yeah, what condition is strong enough? All right, I will get there. The reason first I explained why it's not strong enough. All right, nobody in the world can prove. When we talk about that, that's nobody in the world alive, right? Alive. Okay? Yeah. So available at this moment, right? We talked about those people. Those people cannot improve. Nobody can improve. But think about it. Not strong enough, because for some hard problems, our current generation, we cannot improve. Can you imagine our future generation can improve? Right? Our future generation, after hundreds of years, people smarter, better than us, they can improve. How about that? Right? That's why I say not strong enough. Okay? Yeah. Consider Fermat's last theorem. Fermat's last theorem. Have you heard of that? Some movie, some documentary movie, last theorem. There is a Princeton professor solved this problem in 1995, but after this problem raised after 300 years. 300 years. Some hard problem, people, we need hundreds of years to solve. Okay? Yeah. All right. So that means our future people can do, in general, can do better than us. Because they can use all the theory that we developed. Okay? So they continue the development, new theory, right? New theory. Yeah. So not strong enough. Then how to make strong enough? This time, strong enough. Then here, our answer is how to be strong enough. We strong enough. We solve it with rigorous proof. That's strong enough. This rigorous proof. Okay? Yeah. Must be a rigorous proof. So, all the experts in the world, they agree on it. Okay? That could be wrong. That's still, even with that standard, that could be some small mistake. But you know, we just try our best to, to make it rigorous proof. For that, from us last year, the first proof was given in 1993. 1993, but there was a big hole. Okay? Big hole there. So then that professor withdrew the paper. Okay? Submitted, then withdraw it. Okay? Because there is a big hole. Some other experts found it. Okay? You had to fix it. You had to fix it. Then this professor spent 2 more years. How many? 2 more years to fix that big hole. Okay? And the final version, 1995, so then it was a solid version. Okay? All experts agree it's a rigorous proof. Okay? No hole. All right. So you can see sometimes people make mistakes. Okay? So we need all the experts in the world try to, criticize it. Okay? Try to find the holes. And the final version, so then we treat as a rigorous proof. That procedure we treat as strong enough. How about that? Strong enough. Okay? So you need, right now the internet era, so we just post on the internet, ask all people in the world to criticize it, okay? To do experiments, to criticize it. Okay? The proof we post, all experts in the world criticize it. That's strong enough. Okay? Strong enough. All right. Yeah. So that's the explanation of question number 3. Number 4. Which of the following ways is the best to describe overall efficiency? Not the best, not the best. They are too optimistic, okay? If you use the best case efficiency. Not the worst, because you are too pessimistic, okay? So, best answer, average case efficiency. Average case, because we consider all the possible cases, then we take the average. But for the calculation of average case, not that easy. Okay? We did it for linear search. Remember, we did it for linear search. But for many other questions, we didn't do average case computation. The reason is relatively more complicated. So we skip that computation. But later we will do some more practice. Later, when we learn binary search, then we will do another special average case computation, binary search. Because binary search, that's the, when you take average case, it's not a linear case. Currently, the linear search, the average case is quite linear. The case is distributed in a linear way. Linear means the cases, the efficiency numbers distributed in some linear way. That's easy for calculation, right? For the binary search, it's not a linear way. Okay? This way, okay? Exponential functions like that. Like that. All right, yeah. after midterm. After midterm. Probably after that. Around before after that, because midterm just next Thursday. Next Thursday. So definitely after that. Pascal's triangle. I mentioned that Pascal's triangle. You can search the web, so if you forget. In class, I showed how to derive that Pascal triangle. Shoulder numbers and two numbers on the shoulder triangle. It's the last one. Here you can see, although for this class, whenever I have some chance, I expand your background a little bit, related background a little bit. Some of the information you cannot find in the textbook, okay? Because I feel some information is very useful. So I want to add it. Here, this is Pascal's triangle. The next one, so this one, I give you the hint in class. Remember, the idea is very interesting. The idea, we reduce the problem size. That 500 number, this number is not very important. Okay? Just some, arbitrary number. Okay? Very, not that important. So, we can change. So, in our analysis, we can keep reducing this number until the smallest number we can reduce, that's 3, right? That's 3. Okay? If you still continue reducing, then we get problem. Okay? Because our problem reduction, we want to preserve some problems. Okay? After reduction, we still want to maintain the original properties. So that's size 3. Okay? 3, you need to find the one, not the maximum, not the minimum. In 3 elements, that means the one you want to find is the median of 3, right? Median, not the minimum of 3. Median, not the maximum. So you find median of 3. 3 elements. Okay? You can see the number of comparisons for the median of 3 elements, the worst case. They're not giving me the best case. Some students give me the best case. 2 comparisons. You can find median of 3. That's the best case. But not the worst case. Yeah. So remember, so here another important point. Because from this question, I did not say worst case, best case, right? I did not say it. Worst case or best case. I do not say it. If I do not say it, which one you should use, worst case or best case? If I do not say anything, you should use the worst case. Do not use the best case. But some students, I saw before some students, if I do not say anything, they use the best case. So here let me explain why the worst case is better than the best case in this situation. Because if we can solve the worst case, then we can solve other cases only better than the worst case, right? You can only do better for other cases than the worst case. Okay? Then your worst case number tells people I can do no worse than this one. No worse than this one. For all cases, I can say that, right? I can solve this problem with this number of comparisons. No exception. You can say that. In other words, I find the whole solution, complete solution. You can claim you get a complete solution. Okay? If you solve based on the worst case, you can claim you have a complete solution. But if you solve based on the best case, you cannot claim you get a complete solution because you didn't consider other cases. Okay? Other cases, the numbers will be lower, will be worse. Okay? You only find part of the special solution. Part of the case is special solution. Not all solutions. So we can only treat as partial solution. Right? Not a full solution. Yeah. So here I like to give you that point. Okay? If I do not say clearly, because many times we don't want to say worst case, right? Because if I put worst case, get you confused. Okay? Get you confused. Why you put worst case? Okay? But if people do not say this worst case, question.
So I just want to make sure I understand. So for a subset of 3 elements, the worst case is 3 comparisons and the best case is 2 comparisons. Is that correct?
Correct. Correct. Okay. Worst case 2 comparisons. Sorry. Worst case 3 comparisons. Best case 2 comparisons. Give you a thinking question. How about average case? How about average case? Because sometimes it may not be 2 plus 3 over 2. It may not be that simple. Okay? It may not be that simple. So when you consider average case, you need to do really in a careful way. Okay? You need to consider the probability issue. Probability. What's the probability for the best case? What is the probability for the worst case? Right? Then you take a weighted average. You cannot assume probability for the best case 50%. Probability for the worst case another 50%. Then weighted average 2 plus 3 over 2. So you need to study what is the probability. All right? So be careful when you work on the average case efficiency. Let me leave this topic after midterm. Okay? Before midterm, let's do not worry about that. Okay? Do not worry about average case. How to calculate in the right way. So we leave it after midterm. When we learn the binary search, let us do the calculation. Okay? I hope at that time I show you how to calculate. So for this question, finding the median of 3, best case, worst case, how to calculate average case. How to look at the probabilities. All right, next question. This one, with the coefficient first, I hope you can identify the coefficients given special, not arbitrary, Pascal's triangle. I hope you can connect with Pascal's triangle. Okay. That's not enough. That's just the first step. Pascal's triangle, that's the first step. So your knowledge base, you have this knowledge, 1 plus x to the 5th power, that's p of x. That's, Pascal's triangle. This is by binomial theory, okay? Binomial formula, or Newton's formula. Some people call it Newton, because Newton discovered this formula, okay? Some people call it Newton's formula, or binomial formula, okay? knowledge in your discrete math. Discrete math, you should learn this topic. Okay? Then, from here, then you apply repeating experiment. Okay? The first multiplication, okay, you get a square. That's the first multiplication. Okay? Second, repeat, square, square, yeah. Next to the fourth, second multiplication. Third, the last one. Yeah. 3. Okay. The minimum. Minimum. People can do it. That's okay. 3. Number 8, we want to sort 3-element array with distinct values. How many comparisons do you need to sort this array for the worst case? You need to, work it by yourselves, do comparisons. Answer is 3. So, worst case, 3. Here, I'd like you to compare with our previous question, median of 3, also 3 comparisons. Median of 3, sorting, median of 3, because if we can sort array, then you can find a median immediately, right? If we spend 3 comparisons, we can already sort it. After we sort it, we can just pick the median immediately. Here. But the same number of comparisons for 3 elements. Be careful, only for 3 elements. When you have more than 3, then finding the median, we always need fewer comparisons than sort. Because we're running to sort it, right? Finding the median, why you need to sort the whole array? You do more than necessary. You overdo it. You overdo it. Okay? Yeah. Later we will get to more details. Median and sorting, 2 different problems. Median, selection problem. Sorting problem. Okay? Yeah. Later there is another very interesting questions. Here I can give you, so if you are interested, you can try by yourself first. Later I will show you the solutions. Median of 5 and the sorting 5-element array. These 2 very challenging questions. Median of, so the first question, find the median. First, you know the meaning of median, right? Meaning of median. Okay? Given an array, after you sort it, you pick the one in the middle, that's the median. But you assume that after you sort it, do not, so given an array, before you sort it, you pick the one in the middle, that's not a median. Okay? Before you sort it, you pick the one in the middle. We do not call that the median. Only after you sort it, the one in the middle is the median. Okay? All right. Oops, sorry. Yeah. Find the median of 5 elements. That's the first question. The minimal number comparisons for the worst case. If I do not say that, that's the minimal number comparisons for the worst case. That's our hidden words. Hidden words. We do not say it, but we mean that. Okay? But the first question, if you want to try, very challenging. Okay? So what do I mean challenging? You need at least 3 or 4 hours if you want to spend time. Even that is hard. Okay? The minimum 3 or 4 hours work. Okay? The second question. 4. 5, 7, 8. Okay. These two, very challenging. Oh, that's
I feel like I remember in the notes there was something about how when it comes to sorting, the best, worst, and average case are all the same. Is that correct?
bubble sort,
But just
bubble
bubble
sort and selection sort. Those two.
Okay.
Best case, worst case, average. Just only one case. Okay? Yeah. But only bubble sort and selection. In the general case, different. Huge difference. So here I can give you the answer, quick answer. The first question, the answer is 6 comparisons. 6 comparisons, the best you can do for the worst case. The second question is 7 comparisons. The best answer you can get. Okay? And we can prove it's the best. The 7 comparisons, we have a rigorous proof. 7 is the best answer. That means nobody in the world can use 6 comparisons to solve the second problem. Nobody in the world, even after 500 years, nobody can use 6 comparisons to solve it. Because we have a rigorous proof of that. Okay? All right. Still a few more questions. I hope I have time to talk about homework. We talk about the problem size concept. True that always mean false. False. Okay? Yeah. Is it true? No, not true. Because there is a special case of magnitude. Right? Think about the magnitude case. Magnitude case. Magnitude case, prime factorization. Is it magnitude case? Yeah. So here, example, the prime factorization problem. Okay. Another is the GCD problem. Find the greatest common divisor. GCD problem also magnitude. Okay. Last question. Yeah. Repeated cubing, repeated. So here the question, can we say that repeat cubing technique always performs better than the repeat square? We cannot say always better. Why? The answer actually is very easy. You consider the structure. Okay? When n equals 2 to the k or close to, or close. Okay? These two cases. When n equals power of 3 or close to it, this case, repeated squaring better. Better. In this case, repeated cubing better. Okay? Yeah. Then something in the middle, it's hard to say. Okay? Something in the middle because it's hard to draw a line. Very hard to find a line between them. Okay? Above that line, repeat squaring better. Below that line, repeat cubing better. There is a line, but hard to find it. Okay? Hard to find it. You need to do experiments to get that line. Right? Yep. All right. So here, yeah. So we these two quizzes, I hope at least I can give you a hint for one question in homework. Okay? Does anyone want to ask me? I hope you pick hard question. Okay? We pick a hard question. There is one. There is one. Do you have any idea? So let me ask you. Let me ask you. Yep. Assignments. Look at this. Oh, I don't want to. Yeah, that's. This question, do you have idea how to solve it? Yeah, this one, all right. Number 22, given 9 elements, it is known that X5 is not in place. What is the maximum number of inversions in this array? Do you have idea on this one? I'd like to give you some hints. Only 5 minutes. We don't have 5 minutes. Larger? Oh yes. Not. The font, not larger. Oh. Yeah. Okay. Let me enlarge it a little more. Yeah. All right. Yeah. All right. Okay. Yeah. So here, the first step to solve this problem, first step. First, we remove that condition, X5 not in place condition. That, because remember, sometimes when we remove one condition, we can make it simpler. Later, then after we find the solution, we add it back. How about that? Okay? So let's remove it. We do not consider X5 not in place. It could be in place. All right? Then, can you answer this question? The maximum number of inversions.
I believe the maximum number of inversions is when it would be like completely out of order. So like it would be like 9, 8, 7, like that.
All right. Good. All right. So let me say this way. The order of the array elements descending order. Descending order. That corresponds to the maximum number of inversions. Because why? All pairs are inversions. In that case, you can pick any 2 elements, all pairs, any pair. Well, you consider any pair you pick, it must be an inversion. So you can calculate. Okay? 1/2 times n minus 1. Okay? You have a formula. But that order, descending order. Yeah? Remember that, descending order. Okay? Yeah. That's important. Then, because we remove the x not in 5 not in place, now we can add it back. This time we do not allow x5 not in place. Now you look at the descending order. Is x5 in place in descending order? X5 in, yes, right? Yeah, in place. That means this maximum number cannot be our final answer. Because this corresponds to the in place case. Okay? In place case. So in order to get our final answer, we need to make x5 not in place. Okay? So the last step you need to make x5 not in place. But remember, 1/2 times n times 8, 4 times 9, 36, right? The maximum number inversion is 36, right? Yeah. But after you make a move, you have to make a move and put an x5 not in place. After you make that move, this 36 number should be reduced, right? They cannot stay in 36. Think about that. After you make one move. So it has to be reduced. Now you need to think about the minimum reduction. Is it possible to make a minimum reduction? Because the minimum reduction, that's the best you can do, right? Look at the logic. After you make some move, okay? Let's say one swap operation. How about that? One swap operation to make the change. Can you make the reduction? You only reduce the inversion by 1. Is it possible? By one swap. If you only reduce by 1, can you say that's the best solution? Think about that. A hint. Okay? Yeah. If you hard to follow, well, go back, look at last few minutes of this video. Okay? And keep thinking. Look at the last few minutes of the video and keep thinking. Yeah, because here you do not have enough time thinking, right? You do not have enough time thinking.
The quiz which you explained, it will be on the